Okay, good morning and welcome to OARC 32B, OARC's second online DNS workshop. I'm Keith Mitchell, OARC President. Before we start the proceedings, I just wanted to run you through a few quick slides with some information. OARC's mission statement. Why is OARC here? OARC is here to make DNS operationally, the internet's DNS work operationally better. As most of you attending today are members, I'm not going to run you through every single one of these, but I think the important thing is that we're continuing to do this in the current pandemic situation, and what we're doing is at least as important in that, in terms of measuring unusual events, keeping the internet's DNS operationally functioning as it ever is. And we appreciate the support that we get from our members, which is continuing to be strong throughout all of this. This is an online event, so I want to remind you that OARC's conduct policy applies. It applies at our online events just as much as our physical events. When you registered for the event, you committed to that. Please be respectful of all the other participants. The meeting is being recorded. The talks will be available in a few weeks on the OARC YouTube channel after the event. Because we're in Zoom webinar mode, if you were not a speaker or crew member, then you'll be muted during the event. We have introduced a new chat platform. I'll say a little bit more about that in a minute, but that is the main channel for public participation and remote participation in the event using Mattermost. So if you haven't signed up for that already, you can do so. I encourage you to do so. Social media hashtags are OARConline and OARC32B. The chat platform Mattermost. OARC has been using Jabber as its chat platform since pretty much since its inception. We found it useful for a whole bunch of things: remote participation in events like we're doing today, back channel coordination of the event, providing a real-time place where if things happen DNS operationally, there's a chance to for our members between various organizations to work in that. Private channels for OARC members' activities is something that we can now support much better. And we've been using it for several weeks now, Mattermost, for internal staff and board remote working support. And it's finding that it works very well. There are a lot of chat platforms out there. So why do we use this particular one? It's open source, it's cross-platform, there's clients for a lot of different, pretty much all the operating systems that you might want. It's provider neutral. We're not locked into any single cloud provider providing this service. We can move it around or self-host if we want. It's also used by a lot of other organizations in our space as well. If you are not an OARC member, there's public sign up for workshop participation and general chat. There's where you can download all the clients. One of the things I want to be transparent about is that this is a service that we're buying as a managed service rather than running it internally. The provider that we've chosen to do it is Mythic Beasts, who are a UK operator. We got them to sign up as an OARC supporter. We want OARC members, this is really important, to feel that when they're doing their operational chat, it's potentially sensitive information. We don't want to feel that it's being logged by some third-party faceless large cloud provider. Mythic have signed up to the OARC participation agreement, so the content is bound by all the strong confidentiality requirements in that. However, we will not be using Mattermost for questions during the webinar. We'll use the Zoom question and answer facility. You will see on your Zoom screen a Q&A box. If you want to ask a question, type into that box. One of our chairs will then read the question out to the speaker, who will then answer in time. They will obviously be first come, first served. Also, please ensure that you identify yourself, name and affiliation when you're asking. If there's something which isn't to do with asking the speaker a question, you need some help with workshop logistics, you can do that in the Mattermost channel or use the raise hand facility in Zoom. That is all I have to say for now. We have two members of the OARC program committee, Ralph Dolmans and Anand Dudahev, who are chairing today. So I will now hand you over to Ralph, who will be introducing the speakers in the first session.
All right, thank you, Keith. So yes, Ralph Dolmans here as OARC PC member. We have selected 4 interesting talks for you for today, with the First one being from Willem Toorop. Willem has done research on the current state of DNS resolvers and RPKI protection, and he will talk about that. So Willem, if you can please start sharing your slides.
Yes. Let's see.
All right, I can see this. Thank you.
This looks good. Okay.
Yep, looks good to me.
Yes, well, this presentation is actually about a research project by two students from the System and Network Engineering Master from the University of Amsterdam, Erik Dekker and Marius Brouwer, who looked into route origin validation and how it is protecting DNS resolvers on the internet. And they did this research in January this year. And so what's this about? Well, we DNS people have provided a security means, DNSSEC, by which you can be sure you have the correct answer for a certain name, provided the domain name is DNSSEC signed and the requester is DNSSEC validating. But DNSSEC does not help when connecting with this address. Right? If you connect, the browser looks up a name and then connects to that address, but that address itself can be hijacked. How does that work? Well, with BGP tricks, a malicious AS may announce a prefix it does not own, and traffic will be routed to the malicious AS if the path is shorter or if a malicious AS announces a more specific route. So illustrating in this picture, someone in network A wanting to connect to an IP address in network B will be wrongly routed through AS5 because AS666 announces 8.0.0.0/24 prefix, which is both on a shorter path. It's also more specific than the /23, which is announced by network B or by AS4. So the IETF developed a protocol which is called Resource Public Key Infrastructure, and it tries to deal with this by letting network operators cryptographically sign and validate prefix and origin data, which so-called route origination authorizations. How does that work? Well, on the picture, AS4 has signed such a route origination authorization, which I will now abbreviate to ROA from now on. And this ROA states that 8.0.0.0 will only be announced by AS4 and will only be announced with a maximum prefix length of 23. So AS1 in the picture does route origin validation. So it verifies that what is stated in the ROA, that is what it sees, that it's correct, conforming to that ROA. And it only accepts the route to 8.0.0.0/23 via AS2. AS666 can no longer attract traffic by publishing the prefix directly because it needs to be announced by AS4. So it needs to add a fake AS4 node, lengthening the path. And it also cannot try to attract by announcing a more specific, as the maximum length in AS4's ROA is /23. So RPKI does not protect the complete BGP path. There's another standard also developed by the IETF which does this, which is called BGP-SEC, but it's not as widely deployed as RPKI. So RPKI is not complete rock-solid security like DNSSEC, but the more ASs sign and validate, the better it works. And also, if the path is short, that also helps with RPKI. Okay, perfect. We have DNSSEC protecting the name to IP mapping and RPKI making sure we connect to the right address. But what does this have to do with DNS resolvers? Well, it's quite common that a resolver is not in the same network as the by route origin validating protected requester. So if the resolver is not protected, it might consult via address hijacking a malicious authoritative, which provides a fake address answer. And that answer might be perfectly validly signed with RPKI or not be signed at all. So the client in network A will connect to it, even though network A is protected by route origin validation. Note though that for this to work, the looked up name needs not to be signed with DNS-SEC, or the network needs to be using a resolver that's not DNS-SEC validating. Unfortunately, loads of second-level domains are not DNS-SEC signed, so that's quite common. So this is a interesting academic attack. Does it really happen? Yes. Well-known example of this kind of attack is the Amazon Route 53 hijack on the 24th of April in 2018, which via the hijack took over the etherwallet.com domain with as a goal to steal Ethereum cryptocurrencies. So we invited students from the System and Network Engineering Master from the University of Amsterdam to look into this. And Erik Dekker and Marius Brouwer took on the challenge. They formulated the main research question: what is the state of route origin validation on DNS resolvers? And they formulated two sub-research questions. Does the length of the AS path matter? And how does Anycast influence the protection? So to test, they set up two authoritative name servers for two domains. One of the domains, valid4.rootcanary.net, is served on a valid prefix, and the other domain, invalid4.rootcanary.net, is served on an invalid prefix. And the invalid prefix is invalid because it has a ROA associated with it that says that the prefix is announced by AS0, which does actually not exist, so it's invalid. The valid domain has a DName configured named invalid, which will redirect a resolver to the invalid domain. And the invalid has a wildcard providing an answer. And in this way, a query for a certain random name, but below the DName name, so below invalid, would be ultimately answered by this wildcard if the resolver is not RPKI validating or route origin validating. Or if it is protected, it will not result in an answer. Furthermore, the random name or the identifier below the invalid here, below the name of the DName, will be seen at both the valid prefix and the invalid prefix, so they can be associated. That's the whole purpose of this setup. Then a RIPE atlas measurement was scheduled with each resolver on all probes sending uniquely identifiable name below their DName. RIPE atlas is a measurement network consisting of more than 11,000 probes, which are handed out at conferences and other events that people connect to their network. The probes get the resolvers in the host network just like other devices would. Those probes can be used to schedule queries at their resolvers that are learned via the HCP, which can be used for measurements. And they can actually do a lot of other kind of measurements, but that's out of scope. If you host a probe, you get credits that you can spend scheduling measurements in the RIPE atlas network. Here's a closer look at the measurement. what's important to notice here is the $R-$T-$P.invalid, which was the DNAME record in the valid zone. So $R$T$P will be replaced by the wipe atlas probe before it sends out the query by random hex stream -timestamp -probe ID. So here is the resolution in more detail. So if the identifier random -timestamp -probe ID is seen at the valid authoritative but not on the invalid, then the resolver is considered protected by route origin validation. If it is seen by both the valid and the invalid authoritative, then the resolver is not protected. Furthermore, those authoritatives are hosted on a beacon that does its own BGP. So we know the AS path towards, but not from the resolver. So it's an indication of how traffic from the authoritative to the resolver might flow, because traffic on the internet is asymmetric, right? So we don't actually know the path from the resolver to the authoritative. We only know the other way around, but we considered it a reasonable metric nonetheless, since there is no way to determine the BGP path from the resolver to the beacon. Also, this model of stub resolver authoritative is too simple and not representative of what happens in the real world quite often. The resolver could actually be a gallimaufry of forwarders and fallback resolvers. But for this measurement, it doesn't really matter. As long as the query is not seen at the invalid authoritative, it's reasonable to consider the ASs on the BGP path towards the IP from which the query was seen at the valid authoritative as potentially route origin validating. Yeah, I leave it with this for now. So the beacon with the valid and invalid prefixes was kindly provided by Job Snijders from NTT. Thank you, Job. And wipe atlas measurements with superpowers using all the probes going on forever, doing the measurement every hour was kindly provided by Emiel Aben from the RIPE NCC. Thank you, Emiel. So Erik and Marius did these measurements reliably, so they had a few attempts before this date, from the 23rd of January till the 3rd of February. And this was perfect timing, because in those 12 days, the number of probe resolver pairs that did do route origin validation rose from 7 till 15%, which can be seen on the left graph. On the right graph is shown how well wipe atlas probes were protected, so more representative of end users. Probes have on average 2 resolvers configured. On the 3rd of February, 17% of the resolvers had at least one of the probes had at least one resolver that was doing route origin validation, but 1/3 of those probes had also another resolver which did not do route origin validation. So realistically, fully protected were only 11.5% of the wipe atlas probes. On the left, the ASs of the top 10 most popular resolvers on wipe atlas are shown. 30% of all queries came from AS 15169, which is Google. But all those queries reached the authoritative on the invalid prefix, so no route origin validation whatsoever. The second most popular is AS 13335, Cloudflare, which only 1/4 of the queries reached the invalid authoritative, and 3/4 of the queries did not reach it. So 3/4 of the queries coming from Cloudflare were protected by route origin validation and 1/4 not. The only other resolver from the top 10 that did 100% route origin validation is AS12322, which is free SAS French ISP. On the right, you see the AS numbers that did route origin validation, sorted by most protected ASs. So number one is Cloudflare, number 2 is FreeSAS, the French ISP, number 3 is Accessful, which also does 100% route origin validation, like all the others seen in this graph. So one of the sub-questions was, does the length of AS path matter? This graph shows the number of protected and unprotected queries per OS path length. Yeah, well, it doesn't, we cannot see a clear correlation between path length and protection. So that was answered. The answer to that question was no. Second sub-research question was, how does Anycast influence protection? And for this, the distinct Cloudflare prefixes were counted. We assume that each Anycast node uses its own prefix. There were 160 distinct Cloudflare prefixes identified with the queries. During the measurement period, we could clearly see that Cloudflare was deploying route origin validation on the various Anycast nodes. Because in the beginning, it was almost none of the prefixes were protected, but on the 3rd of February, slightly more than half was protected. So Erik and Marius did all analysis only looking at the alternatives. I'm also the maintainer of another project, which is called DNS-OARC. And this is a project measuring all sorts of different aspects of resolvers on Wide Atlas, but like QNAME minimization and DNSSEC validation for all the different algorithms, etc. So I added their measurement also to the DNS-OARC project.
This is the timekeeper. You have 7 minutes.
Okay, thank you, Anand. That's enough. 7 more minutes. Anyway, these are the results measured with DNS-OARC over the last 6 months. So with DNS-OARC, we process Wide Atlas results, and we do only that. We do not look at what happens at the authoritative. So we evaluate the route origin validation as follows. If there was an answer, then the resolver is not protected by route origin validation or considered not protected. If there was no answer, then it is considered protected by route origin validation. So this is not very precise and not as precise as what Erik and Marius did by looking at the traffic at the authoritatives, because it also marks resolvers that cannot do any query, which do have resolvers that do not work at all. Those are also marked with this method as route origin validation. But the more prominent error factor is that it also, the resolvers which are forwarding to other resolvers or are part of a fallback group are also not considered. So this graph shows from which ASs with route origin protected resolver came over the last 6 months, but the measurement from which is determined what IP reached the authoritative is a different one than used for the RPKI measurement. So there's a certain leakage of ASs that do not do route origin validation, but still show up here a little. Erik and Marius had a very short period to perform their research project and limited their scope to IPv4, but we also set up domains for IPv6. And so for the record, here are the IPv6 domains and the prefixes. And here is the wipe atlas measurement doing the IPv6 measurements. And here's the graph showing the AS is seen at the authoritative of resolvers that were not able to resolve the IPv6 query. So doing IPv6 or were considered IPv6 route origin validation. So the big bump from the last week of March until half April must be caused by a rounding mistake, which made one of the prefixes used in the IPv6 measurement unreachable for part of the internet, because it doesn't make sense. Those parties listed in the bump are not doing route origin validation. But if we leave this bump out, then we can say that IPv6 is a bit less protected than IPv4, 10.7% versus 14.9%, but the parties involved or which are doing validation are more or less the same.
Timekeeper, we're now into question and answer time, so you need to hurry up.
Okay, so here's what we see with DNS thought for Cloudflare. I think it's interesting to see that we can see with DNS thought also this initial growth in January and February, but route origin validation did not grow further with Cloudflare. It declined for a month and then grew again. Also, IPv6 is not 100% protected. This is different from a ISP like FreeSAS, which has a more binary behavior. Either everything is protected or nothing. So if you want to have a look yourself, you can go to the DNS Thought webpage, which is shown here on the bottom of the page. And also, this is the last slide. This is also contains a link to the report from Erik Dekker and Marius Brouwer. And I still have a few minutes left to answer questions, if you have any, I think.
Thank you, Willem. Are there any questions for Willem? Please ask them in the Q&A panel. We have no questions yet. I'll give it a few more seconds in case anybody's typing right now. It seems that there are no questions for you, Willem, so it must all have been very clear. Thank you for your presentation.
You're welcome. Okay.
The second speaker is Wes Hardaker, and Wes is going to talk about his LOCALROOT project. And I can see your slides. Thank you.
Good morning, everybody from California, at least. So yeah, I'm going to talk about LOCALROOT, which I've referenced in past OARC discussions, but I've actually never given a description of it here. You might have seen one somewhere else. Oops, go back up one. There we go. So first I'm going to talk about what it is and why you might want to use it, and then the recent improvements that have sort of gone in over the last 6 months-ish or so. And I'll show you some screenshots of what it looks like, and then we'll end with some outstanding questions and future directions as well. So, you know, I'm preaching to the choir here, but you know, classic DNS resolution is an ISP typically deploys a resolver, you know, to handle its client's DNS requests, and then the resolver has to go query, of course, the entire, you know, DNS tree. As you know, the first thing the resolver does is it typically sends that question up to everything, and clearly this is shown without QName minimization, where www.example.com goes and searches through the entire tree until it finally finds an answer. The important part, though, is the cache, right? So once it finds an answer, it's going to cache where com is, where example.com is, so it doesn't have to go back and answer again. Unfortunately, if something comes along and says, well, I actually want to talk to ican.org, for example, well, it still has to walk the whole tree from top to bottom all over again. It'll still keep caching those entries so that if something else comes along, you know, in the future, like exam.com, it won't have to go back to the root because it already has com cached, and it gets to reuse that entry in the cache. So local root is really kind of asking the question, what happens if we can pre-cache, everything? Well, you can't pre-cache everything because that would be more memory than the average server could handle. But, we might be able to cache at least a few zones of interest. So local root is functionally a pseudo cache. It, allows you to cache, for example, the root zone, which includes ComNet, PR, horses, and all the things like that, as well as we actually support some other zones too that we'll get into in a minute. It really is 8806, which used to be RC 7706, which is the root on the loopback. We add a couple of features that the RFC itself does not really talk about, which is one, we actually give you notifications so that your resolver has, cache will be up to date within seconds, as opposed to the refresh time, which is what 8806 would your resolver would go back and query every refresh time seconds. So you should actually get updates fairly quickly. And it's also TSIG protected, which means that instead of just doing an AXFR and hoping that that was secure, you can actually guarantee that the glue records, for example, are also secure, which aren't DNSSEC protected and things like that. So we protect the transfer with a TSIG key. So why use local root besides those that I just talked about? The pseudo caching of the root and other zones allows you to, you don't need to query them as frequently, and we'll see an example of what that looks like here in a second. It protects ISPs from outages. There's been multiple research efforts lately that have shown, longer TTLs, and when you have the data locally, you're protected from outages. If the parent zone goes down, you still get to serve the data. It does faster DNS lookups for TLDs and other lookups. I think most people would argue, at least in this room, that that really doesn't help you much, but it does matter to some people. They really want, faster lookups. Faster NX domain results actually might be a bigger interest to some people because, negative answers make up most of the root traffic. So DNS-OARC just had a diddle run in May, and in 6.7 billion requests to b.rootservers.net, only 1.34 were valid. In other words, 80% were NX domains for TLDs that didn't exist. That shows you the quantity of traffic to the root that is purely junk, and you can answer those much quicker than all of those. Typically, have to go out to the root, so you can answer those much more quickly than if you have local root running on your machine or 8806. And there's some other things that you might want to do. You could trigger events after a root notification change or after zone changes. There's sort of some research, I think, grounds here if people want to experiment. So this is sort of what real world effects look like. One of the first things I did when I started this project in 2019 was, well, what happens when you turn it on? What happens to your outgoing traffic? So this is actually the number of requests per hour. Each dot is the number of requests per hour from my house in January of 2017, it was actually 2017 when I started it, to b.rootservers.net. And you can see that while local root was enabled, there was almost no dots. So these were actually looking for name server requests. I narrowed it down to just name server requests. You can see that there's still a dot in there, right sort of in the bottom, as it's probably querying the upstream server just to make sure that it can get information. But it totally removes a lot of the traffic to the root, which is kind of beneficial. So I'm going to go into a couple of recent improvements. So in the last 6 months, we've actually made a lot of changes. It used to have a beta tag on it. It no longer does. We've added IPv6 support. We've added 3 upstream servers, production servers. 2 are on the West Coast and 1's on the East Coast. We've added multiple authoritative zones beyond just the root. And so the 2 new local root servers there are the big ones. A number of other improvements have gone into play. We support multiple configuration entries. In the beginning, we only supported bind. It'll now export unbound and NSD as well. The 3 upstream servers I sort of mentioned already. Multiple zones are supported as well. So besides the root zone, ARPA and rootservers.net, which are the same ones that are served by the current root server operators, DNSSectools.org, which is more of a test zone than anything else. you can download that into your local resolver as well. I'm looking for volunteers, people that run zones that you think your clients might be interested in having pre-cached copies of it. Do reach out to me. My email address will be on the last slide. But the support's there now for a much more flexible infrastructure that allows me to add in and users to select multiple zones. There's also email notifications. So there's a whole set of user preferences for when you want to get email and what type of email you want. And all of this has then also moved into our production provisioning and service monitoring within our b.rootservers.org infrastructure as well. So it's now professionally monitored in the same way that the rest of our infrastructure is. And then there's been a bunch of UI and documentation improvements as well. And thanks greatly to ICANN for helping support this project. They were certainly instrumental in pushing me forward into making this better. So I'm going to go through some screenshots really quick just so you can see what it looks like. This is the local room homepage. The local root homepage, there's a login button and some major news and things like that. You can see that there was an update in June. You get a list of servers that you can register, with addresses or v6 addresses included. This one only shows the v4. It shows you the last time that we saw a transfer from you, whether it's enabled or active, and then there's a get config button on the far right-hand side. And when you click on the get config button, there's a whole bunch of things that you can do. You can select a particular type of configuration that you want. This is showing ISC bind in the drop-down list, but there would of course be unbound and NSD as well. It allows you to add support for other networks that you want to listen to, that it automatically throws those in a config. And you can see on the right-hand side that there is what zones you actually want to mirror, and it defaults to the top 3, but you can check additional ones as well. And then, after you change anything, it spits out the config. So you can see that this is a config setting for unbound. And if you change the dialog to anything else, it'll immediately update this to the config for a particular other entry. There's a bug in this screen, bonus points if you can spot it. It's been fixed in the real version, but there's a syntax bug. That's not where the syntax bug is, but this shows the upstream 6 addresses of 3v6 and 3v4. So that used to only be one address because I only had one server. It's now 3 servers with both v4 and v6 support. The account preferences, I mentioned that you can sort of specify what you want to get emailed by. So there's a whole email notification system that actually will allow me to do much more wonderful features here in a second that I'll talk about. There are a few things that got in the way in the last 6 months. COVID-19 actually, most I think of us are fairly lucky that COVID-19 has not slowed down our work environment too much. It really did get in the way this time because we had to renumber. One of the things I needed to do before rolling out this version was renumber our major service, because I didn't want to make all of the clients come back and get new config. And by the way, if you used LocalRoot in the past, you do need to come get new config to take in these new examples. In fact, the older server is still running, and I will leave it running until I don't get transfers anymore, but everybody does need to go update their config to make use of the new TSIG key generation, as well as the new 3 additional servers. ReCAPTCHA is actually a pain in the neck. I actually presented LocalRoot at the ICANN DNSSEC workshop, but there were some ReCAPTCHA errors that got swallowed by Office 365 and the spam processing, and result was there was a couple of users that probably couldn't create accounts. Those have been fixed, and it really goes to show all of these security mechanisms that we try and instrument, from DNSSEC to CAPTCHAs to DNS cookies to everything. They're a pain to implement, and they really are the straws on the camel's back, unfortunately, but they have to be done. You can't deploy these kind of services without CAPTCHAs, but it does make life more complex. Outstanding questions. One of the things that I would love to get some feedback on are what other zones would be useful to serve. Again, if you're running a zone that you think would be fit into the guidelines that we'll go over here in a second, I'd certainly love to talk to you. We're currently only planning on serving zones with owners' permissions. There's been debate in the past about sort of this type of project of whether, well, there's a lot of TLDs that you can AXFR from, or other zones as well. In theory, we could support those, but I really only want to do zones that have permission from the owners. And what types of zones are really best, right? You want something that your local users are going to be served. In my house, I probably don't need a ccTLD from the other side of the world because I only have 4 family members, and we probably don't, query countries in Africa that frequently, but I might query the US much more frequently, for example. What are other critical infrastructure zones that you really want to be supportive of capturing so that you can protect yourself from outages and things like that? And then, of course, zone size limits. Clearly, if you're running a small ISP with a small amount of memory, you really can't take a huge zone in the first place. There was a major TLD, or ccTLD, that was interested in this type of technology at one point, but they really wanted to deploy it to their ISPs. You might know who you are. I think one of you is probably here. So ISPs would clearly have the support for rolling out a much bigger, cache of a major ccTLD or something like that. But where is that size boundary line? And I don't have an answer for that. And I would love to hear people's thoughts about that. Future improvements, we do plan to do email notifications on an out-of-date detection if we haven't heard from you in a while. We want to actually help you monitor your resolver and your rollout of LOCALROOT, as well as support some other zones, like I mentioned. Please contact me if I haven't said that enough yet. We'll have a REST API so that you can do, automatic configuration and things like that, as well as some groups accounts and other stuff. So that's the upcoming features. I've done 90% of what I'd hoped to do, regardless of COVID and other things getting in my way. But I'm certainly interested in greater feedback as well as more users. It's very stable. I've had a lot of recent people sign up, and they seem to be happy with it. So if anybody has questions, now's the time. Anybody with questions?
All right, thank you, Wes. We have some questions for you. The first one is from Arif Vurel Butcher. And the question is, how does LOCALROOT behave for serve fill responses? I assume it does not cache that.
Correct, because so remember that this almost acts as if you're an authoritative server, as if it actually does pretend like you're an authoritative server for the zones that are supported. So if there is a serve fail, it's actually from your own server. It is not from the upstream server. So you would actually, because you go talk to them, you'll never get a serve fail from the upstream servers unless you're getting a serve fail during the AXFR. In that case, you do need to make sure to look at your log, but that's where we would actually, our future notification of out-of-date detection would actually sort of cover you there.
All right, thank you. The next question is from Andreas Taut. Plans for LOCALROOT servers in EMEA.
So I don't roll out LOCALROOT servers. It's up to individual users to decide that they want their ISP to have a copy of this. And then I provide the support for making that easy to create configuration and roll out. It would be up to people in those regions to actually want to use this service.
All right, the next one is from Larry Campbell. The question is, what is huge? I assume that's referring to the zone size limit.
Yeah, I don't know. Huge, would be, it's restricted to the quantity of memory. One of the things that I would like to put on the zone list that you saw earlier, this one, where on the right-hand side, when it says select zones to mirror, one of the things I'm thinking about adding to this list is how much memory your server has to have in order to likely support that. That's not a trivial number to come up with because, name server memories actually sort of dynamically vary over time as they're caching stuff. But I can at least talk about the zone file size and things like that, saying, your server should be able to at least, incorporate a zone file size of this size, for example. So right now, all 3 of those zones are fairly small. The root is actually the biggest of them with 1,600 entries or whatever.
All right. Then we have a question from Libor Pelton. The question is, does the majority of NX domain queries on the DNS route come from/through any resolver? If not, LOCALROOT would not help with the M. I think LOCALROOT would not help.
So LOCALROOT will help your local ISPs resolver handle requests to the root that would normally result in NX domain. If a lot of LOCALROOT deployments or 8806 deployments occurred, or aggressive negative caching for that matter, the number of NX domains to the root would significantly drop. That being said, no, everybody would have to be running this for the queries hitting the root to actually decrease. I don't expect that to happen. It's really designed to help you, the local ISP, not necessarily help the root servers themselves. That would require a deployment to the entire planet, which I don't think will happen.
All right, a question from Jotan Frakes. Do you enforce ICP3 and only work with IANA TLDs, or do you allow locals to run alt root strings like .onion or corporate local only zones that are not part of the IANA root? And then he continues with, also, would an alt root system like handshake.org peacefully coexist with this?
So local root is an instance of 8806, which is only serves an unmodified version of, say, these 4 zones, like the root zone, ARPA, rootservers.net, and DNS-OARC. We make no modifications. There are other projects that are talking about other mechanisms for changing things. The Yeti project being one of the first, where they actually changed the keys in their version of the root zone and only serve it over v6. We are not doing that. We are serving the exact same IANA root that the root servers serve as well. That is DNSSEC signed, so we make no changes. So we do, if users want to take the config that this is output and do their own thing, like run private, servers, there's a bunch of corporations that have split zones. They have internal names and external names that are different. That is not part of this project. That is something that individual organizations do. ISI, mine actually, we have some internal names that only exist internally. I'm trying to battle and get those removed because it does cause pain when people transition in and out of zones.
Okay. The next question, or I think more a remark, is from Peter Koch. And he likes to see cost-benefit analysis, maintaining and transferring zone copies versus saved DNS traffic.
Yeah, and so, there's, I don't have hard numbers. I can tell you that, graphs like this one, or for example, are, some showing that there's actually benefits to it just numerically. What I don't have in my analysis is the AXFR size is actually quite large for the root zone. So even though this turned on and it prevented a large number of requests going out, it would depend on, how many of those TLDs that you were actually querying, for example, that, you wouldn't normally have to query. And I don't have raw bandwidth analysis. And that's actually something that I would like to personally research in the future, but I haven't done that yet. So there's a lot of cost benefit analysis that I think could still be done.
Mm-hmm. All right. The questions keep on showing up. We only have a couple of minutes left, so I have to see if we can go through them all.
I was going to say, I
the
think
next one is, yeah, we can have a couple more minutes. It's fine.
I'm fine.
From Brett Carr, if you were to deploy a large CCTLD with rapid updates, I assume you would support IXFR.
Yeah, and actually LocalRoot already does support IXFR because at least on the 3 servers that are providing the backup data, we do support IXFR. If there was extremely rapid updates, we would need to coordinate carefully with that zone publisher to make sure that worked well and was not bandwidth intensive for both the LocalRoot project, although we're well connected, and all the clients that might want to use it. So we should certainly talk with individual people and how frequently they're updating. I don't ever expect to support COM, which changes far too frequently and is too big. That's this definition of huge in my mind. But there's definitely some smaller ones that even if they were rapid updates, that shouldn't be a problem.
All right, thank you. The next one is from Phil Rugnold. Is there any work to figure out what the sweet spot for deployment type, home ISP, IXP, would be in terms of efficiency? Who would benefit most, the end user or the root? And so what benefits, and what benefit in terms of saved traffic?
So that's actually it's very similar to the previous question, where I've done only minimal analysis, like this graph shows, of decreasing the number of queries. It would be wonderful to get a sort of a project going that actually would study in advance of, look, this is how much traffic you're currently sending to the root. There should be a threshold of, we can save you bandwidth or save you time, or actually calculate the true benefits that, like Peter was talking about earlier, for what would you benefit and get out of it? How much time do you save? How much bandwidth do you save? How many requests do you save? I only have preliminary results that are seen in this graph as an example of that. I think all of those things I would love to study myself, as well as get somebody else to study as well. I think having anybody that wants to do that, please reach out to me and we can coordinate.
All right, then the last one we can do. Ray Bellis says, many of those root queries come from Chromium browsers that will be sending via a resolver, not necessarily a question.
Yeah, so the Chromium queries that generate a lot of the junk traffic will get stopped at the local root border, which is nice. Users really won't see much because that's a startup cost that they will see only as Chromium starts up. You know, it might start up a little bit faster, microseconds faster, but I don't think most people are really noticing browser startup times is a happy eyeballs problem.
All right, thank you very much. There are 2 more questions. We can't answer them right now, but we can send them to you via email if you want to take care of them later.
Okay.
All right, thank you very much for your talk, Wes. And with that, we are done with the first session of today. We will now start a 10-minute break, which means we will be back here at 2 p.m. UTC with Anand als as chair. So see you all in 10 minutes.
Hello, everyone. A good day to you, wherever you are. This is Anand Buddhadev, and on behalf of the DNS-OARC Program Committee, I would like to welcome you to the second session of this online OARC 32B conference. For this session, Ralph will be keeping time, and Jan will be keeping an eye on the chat monitor. A reminder to everyone, if you have questions during a presentation, please type them into the Q&A panel, and I will read them out for the presenter at the end. And if you're not speaking, please mute your microphones. So with that, we will start with the first presentation of this half. And this is by Axel Koolhaas and Tjeerd Slokker of the University of Amsterdam. We're going to talk about defragmenting DNS and determining the optimal maximum UDP response size. So, Axel or Tjeerd, please share your slides. There we go. And off you go.
Muting problems, my bad.
Okay, we have a little glitch, but ready. I think we're ready again. Okay.
Okay. Welcome everybody. Hello, my name is Axel Koolhaas. And yeah, I will be presenting my research project, Defragmenting DNS, where we determine the optimal maximum UDP response size for DNS. I did this in collaboration with Tjeerd Slokker, and the supervision was done by Willem Toorop and Roland van Rijswijk-Dij. And we are both security and network engineering master students from the University of Amsterdam. And we did this research at NL NetLabs. So first, some background information. DNS is quite an old protocol. It was developed in the 1980s somewhere, and therefore it has been extended. And eDNS0 is the current default extension. eDNS0 has the UDP message size field, which communicates the response size capability of a resolver. So why is this important? Well, you see, the internet is a network of networks, and not every network has the same maximum transmission unit. So you can try to discover the path MTU, so the maximum MTU you can handle between a path with path MTU discovery. However, path MTU discovery is flawed. It is likely to recommend an MTU which is below the actual path MTU. In this sense, it is conservative. And you also have failing ICMP messages. So when, for example, the MTU hits a bottleneck, it can be that the ICP message that gets sent back can be blocked by, for example, a firewall. So if you send a packet and this is too big, which exceeds the path MTU, then fragmentation can occur. And IP fragmentation introduces fragility to DNS. This is because DNS servers are stateless. So let's say, for example, you query for example.com, and you get a very large response with DNSSEC headers, for example, and it hits a bottleneck, and it sends an ICMP message back. Then the DNS server has no idea of what query this belonged to. So in this sense, it's stateless. So to summarize, PathMTU discovery is unreliable, and DNS is connectionless, which causes problems with fragmentation. Therefore, we aim to suggest an optimal maximum eDNS message size for DNS. So we try to capture this in a research question. What is the optimal maximum, or what's the optimal eDNS message size to avoid fragmentation? And we split this research question into sub-questions. For example, we make a distinction between IPv4 and IPv6 because they are different protocols and different headers, so therefore they must be researched separately. And we also make a distinction for DNS stub resolvers and DNS open resolvers. So we first looked at some related work. Weaver et al. And Van den Broek, they researched DNS resolvers and fragmentation, and they discovered that about 10% of all resolvers suffer from fragmentation-related connectivity issues. So 1 in 10. This is quite significant. Furthermore, other people have researched this before to measure the PathMTU. So Toorop used custom name servers to experiment with different eDNS message sizes, where he had different domains produce different size responses. So for example, if you query 1500.domain.net, you would get reply back of 1500 bytes. If you query 1400, you would get a reply 1400.domain.net, you would get a reply back of 1400 bytes. DNS-OARC also researched this, where they used a custom name server and chain CNAME responses. And their server would send multiple replies, first a very big one, then a smaller one, then a smaller one. So where each reply would decrease in size, allowing them to measure the PathMTU. These solutions were nice, but they both use custom name servers, which decreases their reproducibility. But we did like the subdomains producing different size responses, and we adapted the CNAME trick to DNAME records for our setup to also generate different sized responses. Lastly, for the related work, Fujiwara and Vixie wrote or are currently writing an RFC draft on fragmentation avoidance in DNS, where they make a suggestion on a possible maximum eDNS message size. And this is a quite topical subject since the 30th of June. Vixie asked for feedback on this RFC. So this was just before the release of our research. So we hope to contribute in that sense to this RFC with recommendations. So now getting to our methodology. They say a picture says more than 1,000 words. I hope to do it in less. So this is our measuring setup. So on the left-hand side, you see RIPE Atlas, as described by Willem. It's a platform we use to do measurements with. And we created 4 separate Atlas measurements. One for IPv4, one for IPv6, well, actually 2 times, as you can see by the A and Quad A records, and also 2 in the sense for stub resolvers, as you can see on the paths on top, and for the open resolvers. And I want to give a special thanks to Emil Aben for creating these queries. So as you can see, these are the paths we try to measure. And this brings us to the right-hand side, which is our DNS server. We set up a VPS on DigitalOcean, and we installed NSD on this. And we used DNAMEs to generate different size responses. But we did want to have one universal query. So for this, we used the extended Berkeley packet filter. And this was done in collaboration with Toorop and Karpai. So all the probes, they fire the same query, 1500.domain, etc. And this would enter the interface of the VPS, and this will pass through eBPF, and eBPF would rewrite the query to the MTU we try to measure at that moment. So let's say, for example, we try to measure the MTU of 1440, then eBPF would write the query from 1500.domain.whatever to 1440.domain.net. And this would get then sent to NSD, and NSD would reply with a size of 1440 bytes. This would then get sent back through eBPF. eBPF rewrites the answer to the original query, and this would get sent back, allowing us to measure the path MTU. This brings us to aggregating how we got our results. So we use the Atlas API to query the Atlas probes and get the results from the querying side. And we set up DNS tab to get stateful information about the name server. So this was our methodology. And now I'm going to switch over to Tjeerd, who will be talking about our results.
Yes, thank you. So if I'm correct, you can all see my screen now. Yeah, so the results. Well, what we can see here, what we present here is the graph, which presents on the y-axis the percentage of failed DNS UDP queries, and on the x-axis the MTU sizes we measured. In the table, we do our own suggestions. This is a different value than in the graph. That's because the value in the table is the eDNS message size, and in the graph the MTU size. So the eDNS message size is the MTU minus the IP and UDP headers. What we see for the IPv4 stub resolver is that the MTU size of 1500 feels noticeably more than the other MTU sizes. Then we see that it declines in failed percentages, and then it stays steady at around 0.83 after 1260. That's because of this graph, we suggest to use an eDNS message size of 1372 bytes, which, as I said, corresponds to an MTU of 1400 as presented in the graph. For the IPv6 stub resolver results, we see again that this MTU of 1500 feels noticeably more than the rest. However, in this case, 1492 also feels more than the rest, which is interesting. Then there is this middle group, which feels around the same percentage. And then the last group of 1280 and 1268 feels less than the rest. Based on this graph, we suggest, as a trade-off between a higher data capacity and lower percentage of failures, to use an eDNS message size of 1332, which corresponds to an MTU size of 1380. Then, for the IPv4 resolver results, what we can clearly see here is those three groups. Again, 1500 and 1492 feel more than the rest. Then there's this middle group, which feels around the same percentage. And there's this last group of 1260, 1248, and 1232, which also feels around the same percentage. So based on these results, we would suggest to use an eDNS message size of 1232 for the IPv4 resolver. For the IPv6 resolver, we again have these three groups, but it's a bit less clear to see. 1500 and 1492 are the first group. Then from 5060 to 1300, up to including 1300 is the middle group, and then 1280 and 1268 is the last group. And again, as a trade-off between a higher data capacity and a lower percentage of failed queries, we would suggest to use an eDNS message size of 1332 for the IPv6 resolvers. Then to discuss our results. What we saw in all graphs, of mostly all graphs, is that the MTUs of 1500 and 1492 stand out. They have a noticeably more higher percentage of failed queries. This is possibly due to tunneling and encapsulation of the queries and answers. Then we saw that the IPv6 stub resolver failed around in the middle, failed around the same percentage as can be seen here. This is possibly due to failed path MTU discoveries. As stub resolvers are normally mostly used in internal networks, the failed path MTU discoveries don't play a big role in that sense. So in an internal use, we would suggest to use the 1332 EDNS message size. However, if a stub resolver uses an external resolver or connects to outside of its internal network, then we would advise to use an EDNS message size of 1232. This is to avoid the possible failures of the path MTU discovery. Then, lastly, for the IPv4 and IPv6 resolver results, what we saw, I only present the IPv6 resolver results here, were those three groups. And the middle group failed around the same percentage, and it's caught our attention. It has made us dive deeper into the results. However, we couldn't find a single cause of failure for these MTU sizes. There was no single autonomous system that was causing all these failures. Then some limitations of our research. The MTU support of DigitalOcean. Our research needed to support an MTU of 1500 bytes, as that was the maximum we were going to test. However, we didn't know in advance of DigitalOcean supported it. Luckily, our experiment proved it is supported. Then we have the point of dynamic paths. A network path isn't static, so the route it took the question to arrive at our name server doesn't have to be the same route the answer returns over. So that way we can't draw definitive conclusions on the arrival path, as we have no influence on this path. However, we had to use this path to be able to determine the failed resolver queries, as they try to reconnect over TCP if UDP fails. Then there's a percentage of failing probes. These do, however, not impact our final conclusions, as it's a rather constant quantity. Then we also have the RIPE Atlas bias, and that means there's a bias in the results, as the distribution of the probes is not equally divided over all countries and does not completely represent the entire internet. This is because the probes are mostly located in Europe and North America. Then lastly, there you have the measuring period. The graph we presented, the data we presented you, is 2 weeks of aggregated data. Then to conclude our research, we tried to create a reproducible environment which is publicly available to answer the question, what is the optimal EDNS message size to avoid IP fragmentation? So what we found, there's no single EDNS message size which can be chosen. However, if we split the stub and resolver into different message sizes, and also for IPv4 and IPv6 use different message sizes, we can make some good suggestions. So for the IPv4 stub, we suggest 1372. For IPv6 stub, for internal use 1332, and for external use 1232. For the resolvers, we suggest for IPv4 1232 as the message size, and for IPv6 1332. So some future work on our research, that is look into the spread of the probes between and within ASs. So look at the RIPE Atlas bias. Then also possible to look at the failing probes and research what causes them to fail. This could possibly be a DNS block in the network, but it could also be a software failure. And lastly, the continuation of this research. As the internet is always changing, it's important to adapt to the changes. And by continuing this research and look for the most suited EDNS message sizes, we can make DNS perform as optimal as possible. So to conclude our presentation, there is no single magical EDNS message size for all DNS resolver implementations. We, including Willem, are now open for questions.
Thank you very much, Axel and Tjeerd. for this presentation. And we now have about 5 minutes for questions. I see some questions in the Q&A and I will read them out now. First off, we have a question from Victor Duchovny. He asks, have you at domains, I'm not sure what that means there, have you perhaps any domains or have you looked at domains that can only be resolved if the buffer is large enough? In other words, don't set the truncation bit and don't offer TCP.
Yeah, so maybe Willem.
Yeah, I can. So I see that Victor posted a second question which provides further context. I can read it out. He said, for further context, some authoritative servers only work with sufficiently large packet sizes, while studies run their own out servers and don't generally probe what fixed resolvers will encounter when querying many different domains. So this is true. So this research looks at the client side, so to say. What can stub resolvers and resolvers handle, and does not look at what authoritatives can do and provide. I know that my colleague Roland van Rijswijk is looking into this in collaboration with other people. I have to ask precisely. So this will be additional research. Also, but in doing the measurements with Axel's and Tjeerd's method, the resolvers that had a EDNS size or announced the EDNS size or propagated EDNS UDP maximum UDP size lower than the measured path MTU, they would get a reply with TC bit set from NSD. If they would go over or return over TCP, then those results are left out of the counted failures. So they are considered operational correct, so to say. So they might have a smaller EDNS or path MTU, but they can handle TCP, so not relevant for this specific study.
Okay, thank you, Willem. The next question we have is from Fred Baker, who asks, what IETF internet draft did the speaker ask for review of?
No.
Well, no, we didn't ask for a review, but Paul Fixie did on his Twitter.
Yeah, and the draft is called Fragmentation Avoidance in DNS by Fixie in Fujiwara.
Thank you. The next question from Andre Suri. He asks, so is it worth to have different sizes, and how you measured, in other words, are you planning to measure, the impact of just using the smallest number?
To have different sizes.
Is it worth to have different sizes, and how you did the measurement, and the impact of using just the smallest number?
Well, if you pick this, okay, Willem can also go.
So that's not actually feasible to do with RIPE Atlas. We cannot tell the resolvers which the probes are using to use a specific EDNS, small EDNS size. So that we did not do that impact study. It would be interesting. That would be a different study indeed, to see what's the impact of using 1232. This study looks at what maximum path MTU sizes can the clients on RIPE Atlas handle. both the probes themselves, which are the stub resolver results, and the resolvers with which they are configured.
Okay, thank you, Willem. The next question from Ralph Weber. He says, I already forgot the 4 numbers. If you had to choose one, which one would you take?
None. I wouldn't choose. Yeah, to be honest, I wouldn't choose one. I would really suggest to do it dependent on your situation or your implementation, because there is a big difference between an IPv4 stub resolver and an IPv6 resolver. There's just such a big difference, as you can see on the graphs, that I wouldn't just use one value, because for the one scenario, one use case, you will be way higher than you should, and for the other use case, you are way lower than you could possibly go, which would be, well, not really nice.
Thank you. One more question from Paul Hoffman. If you select out probes that have firewall issues with ICMP, wouldn't that change your recommendations significantly?
Yes, it probably would, because the flat middle group is very likely caused by errors in path MTU discovery. But to have a realistic representation of, well, of the internet, of what stub resolvers look like, we should also take along those probes that filter out ICMP messages and thus have path MTU discovery problems.
Yes, and otherwise it wouldn't be a representative sample of the internet population.
Okay, thank you for that. And I think with this, we are out of time. So I would like to ask the presenters to look at the Q&A section and type in the answers to some of the questions in there so that we can start the next presentation. So apologies to those who were in the queue but did not get an opportunity to have their question asked live. So we will go on to the next presentation. And this is by Ed Lewis of ICANN. And he is going to talk about defining a DNS statistical core. Welcome, Ed.
Hello, hello, Anand,
Hi.
and everybody else. We've got a big crowd, I've noticed. Can you see, Anand, before you mute, can you see my first slide and my, oops, let's see if I can switch slides here.
Yes, we can see your first slide indeed.
Okay, you
Yeah.
see me switching, okay, good, okay, well, thanks.
Okay,
All right.
I'm muting myself, carry on.
All right, so I'm here to talk about something which changed names recently. As you see, I crossed out defining a DNS statistical core, which is the name I applied for the speaking slot. And it's now called the DNS core census. And the name changes because we, in talking with some people internally to my work group, the name came last, basically. And so we just changed the name of what we're calling this thing. So the point of my talk, I want to describe a project which is meant to be a resource for research, for researchers, something that you can use in doing other work. It per se isn't an analysis. It's basically just trying to gather information together. What I'd like to do is gauge interest at the level of the audience, which is a little difficult online, I admit that, so maybe follow-ups will be the better way to do that. And I'm kind of asking for a small group of volunteers who might want to poke at this thing. It's kind of in an alpha stage right now, and it could probably use some improvements from other people's eyes and some other things that could be added to it. I've been using it for stuff, and I find that I add things to it now and then, and additions don't necessarily upset the previous projects, but that would happen. So let me get on with this. So the environment that I'm working in is the intersection of the DNS, the protocol and the system and the servers and all this and stuff we talk about, and the domain name registries, which is the top end of the DNS system out there, the operational way we put names into the DNS. I'll refer to GTLDs, and that by that term in this talk, I talk about generic or sponsored names. CCTLDs are what I call jurisdictional-based names. They're the ISO 2-letter codes that we're familiar with, and also the IDNs that have been assigned to that. And also the reverse map. We talk about that now and then. That's the IPv reverse address mapping. Goes from address to host name, basically, and that's just a summary of what that's for. And there are also some other, I call non-celebrity elements that are involved here. What I mean are, these are zones that are in the area of study that I'm looking into, but we usually don't pay much attention to them. It's interesting that they're there. They're kind of trivia. Just about anyone who does DNS measurement analysis, they'll touch this area, whether or not they are dealing with registries or not. They try to look at some of the stuff that goes on in there. For example, in Wes's talk, he said that about 80% of all the queries coming to his root servers are NX domains, and will help us, sort that out by looking at the list of what should be there, what shouldn't be there. So, like I said, this was a research project which came out of a personal need and a long history of trying to do studies on the internet, and I keep rewriting this code. And so some of these are my motivating questions out there. Is the TLD of class 2012 a GTLD? Some people like to do analysis of the new GTLD program that's come out in the past now, 10 or 8 years ago. Another one is, when you look at an IDN for a top-level domain, is it the CCTLD or is it one of the GTLDs? That one was probably my biggest launch because that frustrated me to know what kind of a TLD it was by just not being able to look at it anymore. In fact, just before I did all this work, I scraped the IANA web pages, IANA.org web pages for the root zone database, and found a way of getting the information out, but it was rather tedious and it was flaky because it was reading text. Another one, are there ROA certificates for name server roots? This is kind of the converse of what Willem talked about earlier. This is looking for who signs their authoritative name server paths, and just be good to track that. And I actually have a project that's doing that. And finally, is a name under an expected TLD? And that goes back to, is a name kind of leaked out to the internet when it shouldn't be on the internet? Now, what I'm trying to get to is I'm writing stuff in Python and I'm using JSON, but that's not important really. The idea is I'd like to be able to have some simple code which I import JSON requests, bring in all that standard already been defined libraries. I can read the zone JSON by getting a wget or a curl or whatever your way of retrieving files is. Request.get does this for me. Go out some path, fixed path, pull back all zones.json and just grab that. And then use the JSON loading ability to just pull out all the stuff into a nice large dictionary data structure for use. And so I can say things like print zones example category, and it says, oh, it's an IETF special use. It's one that you don't see on the internet. You print zones ARPA IANA registration date, and it tells you this ARPA was first registered with IANA in 1985. And there's many other examples I have out there. I just wanted to put ones that were very generic in the slides. So my fuzzy idea was I want to start at the root zone and I want to look at the top level zones, and the top level is kind of fuzzy. This is the fuzzy idea again. I want to look at what's the TLDs, the delegation of the root zone. And I've been doing work on that for many years in one project. I want to also look into what's just below the TLDs, like the one I always use cite is that in .uk, co.uk used to be the place where you put all of the company names before they opened up for second level delegations. So I want co.uk to be part of my study and name everything of that sort. Also expand to include the reverse map, because what's happening in the RARs is very much the same as what happens in the domain names in terms of operating the DNS. Because in this case, one thing you might want to study here is how operators put into play the technologies that we have out there. And there are some things that apply to the forward map and the reverse map. I also want to include all of the non-DNS domain names, again, like all the names that are special use, so that when you see them, and you see them on the internet, you know that they aren't supposed to be there, because probably because of an operational opening or something like that. But you want to recognize these things. That's why they're also part of what I'm doing. So what kind of information am I trying to include into all of this? I'm trying to include things about name server, besides the zones, and a lot of metadata about the zones. I'm also going to cover the name servers that they use. We look at name servers where they match top and bottom, you know, the cut points versus the apex of the name server set. Also, and then for each of the name servers, they all use addresses. And the addresses, I look at information about them. And you know, addresses are shared by multiple name servers. Name servers use multiple addresses, and up and down the line, zones and everything like that. So I'm trying to keep track of all those relationships in this little group of data. Now, the meta ancillary information I keep, dates are important, status, what kind of a zone it is category, is it a CCTLD or GTLD, and so on. I go down as far as the routing attributes. I actually grab the route origination information for each of the IP addresses that are said to be serving name servers. What I don't mention there that's also significant is the DNS-SEC. I grab whether things are signed, what the keys are in there, trust anchors, and so on. And after looking at all of this work, I ended up essentially with a census of the conceptual top region of the global public operational DNS. And that's where the new title came into when we finally realized this. Now, census, I go to Wikipedia for my definitions nowadays. And if you go to their webpage on census, it says it's a procedure of systematically acquiring and recording information. And that's kind of what I'm doing here. I'm trying to pull information that's configured as well as I can and just basically aggregate all the information in one place. For example, answer a question like, how many TLDs sign with the DNS security algorithm number 5? Can you count that? See that happen over time. You can do that with this information that I'm pulling. Now, to give you a little bit of what's in the data structure that comes out of this, here's a top picture of it. Now, of course, with data, it goes on forever, and you can't do that in slides, so I'm not going to try. But for ARPA, I'll have the A label, I'll have the U label for just about everything, so that if it's an IDN, you'll see the written script. The category I have is, ARPA happens to be a special snowflake. It's an ARPA zone. It's a little unique. It's active. It has a jurisdiction, which I use XA for worldwide, ZZ for I don't know, and then I try to pull down the 2-letter code that's appropriate for whatever it is. I look at the RNAME field because that tells me something. I pull out the resource record signature information. You can do some analysis on that. And then I have the authoritative name servers list. I have the zone cut trust anchors and anything I can grab and put into this one place. Now, the other part of this is this notion of a census designated place. This is because when I define what I'm going to look at, I don't want to give it a special name. I'm not creating anything. I'm not incorporating a city here. I'm just gathering information about a part of the DNS that we see running together in a very informal way, just for statistical purpose, just for numerical purposes, for counting things. I'm just trying to not establish any meaning by this. And what this is, this census designated place is what I've come to call the core. And the core generally includes the root zone, the CCTLDs, GTLDs as the domain names, the forward map, ARPA, all of the address and routing parameters out there, the V4, V6, and then all of the sub-elements that are related to that. And that's what I consider the core of this to be, because I just assign certain assumptions about what's happening in the core, and I kind of hold those areas to a higher level of operational significance, operational performance than I might for something that's outside the core. This by no means this is the important part of the internet. Like the social media sites are not here, the business relationships are not here. This is just structurally what I call, it's come to think of as the core. So how do I go about creating this? So I started with looking at the public DNS root registry, and there's a place out there you can actually get the root registry in a raw format. And I looked at it, and right away I realized that I had to kind of go up and down at the same time here. So I spent a little bit of time aggregating root registry information, and ICANN publishes maybe about 4 or 5 reports related to the root registry across its property. There's the root zone database. There's the list of TLDs being created for the purpose of IDN CCTLDs called the fast track. There's a list of terminations of TLDs out there, the process of terminating things out there. We have a JSON file which talks about the contracts that we have in existence, or actually that have either do exist or have existed for the GTLDs, and a few other places. I'm trying to think. I could brag that I read CSV, JSON, XML, HTML, and maybe one other format to put this together. It's all over the place. I also pull in the IETF special use domain name registry to just note names that have special status in the namespace above the DNS. Now, for the top level zones, as I start going down there, I try to pull the zone transfers as much as I can. I pull the root zone, ARPA. Some of the RAR zones are pulled over AXFR. Anon knows I bugged him about that. It's also AXFR over FTP. Some of the RARs make their zones available through FTP, and I've been pulling that in, reading the zone file, and converting that into a zone transfer, and so on. I also refer to other parts of this, other information sources out there. I use the Mozilla public suffix list. That helps me find out what's the sub TLD structure for many places. It's a starting point, and I'll talk some more about that coming up. And for addressing and routing, I lean quite a bit on Team Cymru's IP to address number mapping service. That gives me where IP addresses, what are their route originations, who is looking at this stuff, and just a wealth of information. And I also use a lot of DNS queries, generally to fill in the authoritative information, because sometimes the authoritative and the cut point information are not quite synced up, and this helps me just list everything in one place. So one of the things that I've been trying to do here is I want to make sure that my data collection is representative. I want to be able to cover a lot of the top part of the internet that covers all of the operational, not top part of the internet, top part of the DNS structure we have. That covers as much of the range of operations out there, going through different types of models of working with things. I want it to be stable, because one of the big uses for this is for long-term collections, long-term measurements. I want to keep the core members pretty stable. What's considered to be a core element to be pretty stable, not flapping in and out. But I also want to be lightweight. Meaning that I don't want my routine to go out there and soak up a lot of resources just to put it together. Right now, I run it on one machine. It takes 8 hours of the day to put together. It's probably not a high power machine. I haven't thought about distributing it, and that's all for later on. But every day, it's pretty good to have this when I start the day out. I use a lot of bulk data sources and so on. I did find that sometimes being lightweight means you can't always be stable, but that's a detail for those of us who really want to know the details about how you do things. So I also have
timekeeper here. We have 5 minutes until the start of the Q&A.
Okay. All right. Okay. So I'll go briefly on this. I have this thing called commercial registration boundary, which is what's around the edge of the core, and now I'm going to skip over that because that I want just to mention that. So I have an Achilles heel here for those of you who might be interested in what I'm working on. So detecting the sub TLD elements is pretty much kind of just stabbing in the dark in some places. The PSL has candidates that's not always up to date. It's not, it's hard for PSL to stay up to date. I did an informal scrape at one point. That doesn't scale very well. And then I go through different candidates out there, and I've found that there's been fluctuations because sometimes people don't have things properly configured. Now, the fixing that would be to have all the TLDs out there, have all of the TLDs indicate they're sub TLDs, but we're not going to get there. I don't really want everyone's TLD zone file. I have a lot of TLDs already. The GTLDs I have access to, but not the external, the CCTLDs. I know some of them are out there, but I haven't gotten them. Now I have another crazy idea, which I just haven't pursued yet, which is use passive DNS to discover these. I also have another area of work to go forward, which is what do I call these things? Like I have these dates here, and I have GTLD, meaning I get it from one data source. IANA is a different data source. And so as some people will want to work this, we might suggest a better way to call the selector fields within the dictionary data structure. And also there's some other information that may prove to be more interesting to folks than we thought. Currently it's working. I actually have 2 or 3 projects which depend upon it, but I'm not quite convinced it's mature. I have a place, it's semi-secret, semi because I haven't told anybody where it is. But I have, every day I have files out there called all zones, all name servers, all addresses, and I also have a history with a timestamp on it, so you can go back over time to see what was recorded. And So what I'm doing right now is I'm doing an RPK row adoption by top DNS zones. This is the converse of Willem's talk, where I'm looking at the servers. Are they signing their zones to them, not whether whether the resolvers are protected. I do a TLD DNSSEC scorecard, which looks at the way TLDs out there have rolled out DNSSEC over time. And I've done that for a good long time. But I'm still learning different ways to use this census. So when I'm looking for help, if you are interested if you have time to kill, if you have grad students who need something to do, I'd like to see people try to make use of this, give it a trial. You may wind up having to rewrite some of the trial code as we change names of things. But I'm also looking for just a small group of people, because I can't handle a large group of requests coming in for this, because I'm also doing lots of other work out there. So, and so my email is here. And if you try to catch me in the hallway today, I'm going to call the police and throw you out of my house. But, that's the way we normally say we meet these things. So with that, I will welcome questions.
Thank you very much, Ed, for that presentation. We now have a little bit of time for questions and answers. And I see one from Victor Duhovny. Are any CCTLDs contributing stats to your study? Getting data on CCTLDs is often quite difficult.
Yes, I have chosen not yet to try to include CCTLD data beyond what's publicly available. For one reason is that I would like to set up this to be purely authoritative information, stuff that I have the source information to. That's the number one reason. Number two reason is that I would have to start going through ad hoc methods to pull in the CCTLDs that pull in the. I'm sorry, I saw another question come in. The number two reason is that I don't want to have ad hoc methods for collecting CCTLD zone files at this point. I could do that, and number three is actually I'm kind of lazy. I haven't done the ad hoc stuff yet. But right now, no, I'm trying to make this purely about GTLDs, only for the sake of my sanity, but it would be good to have CCTLDs out there. And Victor, you're correct. Getting data on CCTLDs is often difficult, and that's why my dream was to have all this information come into me much easier. So,
thank you, Ed. We have a second question from Dmitry Komanyuk. Do you plan to give feedback to Mozilla PSL about dead links?
Hi, Dmitry. Not explicitly. I have contacted someone who is working with the Mozilla PSL. In general, the Mozilla PSL is a very complicated story. So that something is dead, it may or may not be useful information. It's hard to say, because someone might be relying on being there. What I do, though, is when I do a dig for something, I do a DNS query rather, not a dig. A DNS query for something, I do note I might get back an NX domain, and that's how you find that those like dead places. So we'll see.
Okay, thanks. Then we have a question from Paul Mushene. Please.
Yeah. Yes, I hope so. I'm sorry. I'm sorry, Nan. I'm also have a Q&A pod up.
Right. Okay.
Yeah. I at some point, yes. One of the things I've really tried to do in my code is I want to make this reproducible. I want anyone else to be able to run it. There are 2 points where I get data through a prior agreement, but that everything else is publicly available that I'm doing. And so, yes, I think I would like to have anyone else be able to run this, because they can, and then they can grab whatever information they want out there.
Then we have Hugo Salgado saying that one care that has to be taken with the PSL is that there are sub-TLDs that are unofficial, in the sense that they are not part of the definition of the TLD infrastructure, but private ones that decide to open delegations to unrelated third parties.
Yes, Hugo, that's a good point, and something I've considered. One part of this is that, let's see how. I'm trying to keep the core to be what I consider to be the public area, and because there's a little bit of debate about whether or not there should be other parts of that. And I've decided that it actually kind of doesn't matter, because as long as you collect the data of something, anyone can analyze it any way they want. You pull out what you want. other parts of the PSL not being official, actually, I use it as a heuristic start. I've done some other work to try to add to it, and you know, frankly, if I had the exact answer, my code would run in probably half the time or less. I spend a lot of time poking through the DNS to discover what's out there. I keep my ears open, and I really would prefer this to be all automatic. I mean, that's the only way this is actually going to work. But we do what we can do without, you know, the perfect world out there. So, next.
Thanks. Then we have Jonathan Frakes, who's saying, as a volunteer maintainer of Mozilla PSL, I think he means he's a volunteer maintainer. Would you be open to filing an issue on the GitHub for the things that you catch?
Yeah, I could do that. I could certainly make a list of what I catch. I'm thinking that because in my code right now, it doesn't exactly distinguish between a PSL suggestion and something else, but I could, the code to do that wouldn't be hard to gen up, and submitting that in the appropriate places would be the right. Jonathan, you probably can contact me offline and let me know exactly where that should be. So anyway, you just contact me offline and I'll see what I can do to send in the things at NX domain, whether or not they're, you know, dead or not. Let's leave it up to someone else's question or reasoning. So.
Okay, and we have Puneet Sood saying thank you.
You're welcome, Puneet.
That's done. With that, we have no more questions. So that's the end of Ed's presentation. So at this point, I have some reminders for all the attendees. Dinesh has sent out Zoom invitations to everyone for the social, which will be starting in a short while. So please join that for the socializing, bring your own drink, etc. We have a little bit of time now in case anyone has any pressing questions for any of the presenters today. You have an opportunity to ask a couple of questions that you may not have had. So if you do, please raise your hand, type your question, and we can take them now. I don't see any questions or any raised hands, so I'm going to pass the mic back to Keith Mitchell for wrap up.
First of all, just to say thank you to everybody who makes these workshops possibility. Particularly thank you to VeriSign, who have sponsored all of our workshops online and offline this year. So thank you to VeriSign for their ongoing support as a workshop patron. All the OARC members and supporters that make OARC possible. In addition to, although most of our funding comes from membership funding, subscriptions, we also increasingly have various grants. In particular, we've had quite a lot of success this year with achieving funding for a new data store. We're 18K towards a 20K target, and the deployment of that is underway. Program committee, in particular, Ralph and Anand for chairing today, but the entire program committee make OARC workshops happen. All our speakers, they all do this on their own time. I used to say they did it on their own expense, but actually doing the online workshops, it takes quite a bit more time on the part of the speakers with various rehearsals. So we're particularly grateful for their cooperation with all of that. You want to see more online events, then please consider sponsorship, patronage, or donation via the links that are there. You should have received by email, and it's also in the Zoom room, the online social event invite. So we have an informal event, which is not a webinar, so you won't be able to see and hear all of each other immediately afterwards. There's the meeting ID, the password, which you should get via other channels, is 871210. And we tried a few new things this time. I'm sorry they didn't all completely succeed. In particular, the new rating tool decided to go a little bit sideways, despite the fact that it worked great the previous day. So apologies for that. We will fix that or find an alternative in the next day or so. So on Thursday, watch out for an announcement. We'd still really like to get your feedback on the talk ratings. There's also participant event survey where we want your feedback on the event. That's still working. Please go to that link. The other thing that we tried today was Mattermost for the chat stuff. I'm pleased to say that we have plenty of participation in that. There's a little bit confusion over invites. I think we've mostly cleaned that up. If you're an OARC member, the important thing is to use the same email address as you have in the OARC portal. And whether you signed up today or whether you got previous invite or whether you got an invite and it expired because you were on holiday, we will clean that up. If you think you should have access as an OARC member to Mattermost and you don't, then email admin@dns-oarc.net and we'll sort that out over the coming week. And we'll continue with the public access for future workshops and in general. Future workshops. So what are the plans? Well, who knows what the plans are? We're in a very uncertain world at the moment. We plan to hold further online OARC events until physical meetings are feasible again. What we would like from you in the participant survey is feedback on how often you would like to see these online events, how long the online events would be. We're also interested in what would be acceptable conditions for you to do future physical workshops so that we can have some idea of when we go back to them. But clearly we're as uncertain as everything else in life at the moment with the pandemic developments. What do we have planned? OARC 33 will be an online event. This was the workshop that was originally postponed from Paris in May. We still have plenty of content for that, which we'll be using, but we will be having a shorter workshop than a physical one. We're not going to make you sit through 2 days of Zoom. It will be at least 4 hours of content, so it will be a longer format than this event or the previous 32-hour workshop that we did. It will be centered in European time zone because that's where we originally wanted OARC 33 to be. The CFP is now open, so we're accepting presentations for that. In particular, we want to see the updated and timely stuff. For OARC members, we will be having our AGM the day after. Again, that will be online on the 29th of September. We will be using a new tool to allow online voting for the various AGM elections and resolutions. You can find the full details of the AGM there. In particular, we are looking for nominations to the OARC board for the board elections that will take place, and the deadline for that is the end of August. What are we doing for OARC 34? We really can't say. It might be a physical event. It will certainly have a virtual element. We may have some kind of hybrid. The original mooted date for that was the 5th of February. And the exact format and date, we'll just have to see how things go between now and then. We're tracking the plans for what Nanog 81 do because we were originally planning to co-locate there, but it's extremely difficult at this point to say with any certainty what the plan is. Again, your feedback will help us make the best decisions. And again, for those of you who are not OARC members and you found today's event useful and helpful, please consider becoming an OARC members. Here are some of the benefits, but we have a very unique and informed community here, and I certainly invite you to participate in it. That is all I have to say. That ends the formal part of OARC 32 today. With that, we will end this webinar. And we will hopefully see you in the social event space in a few minutes.